Okay, so hello, good day again. It's April 15th, 2020, online lectures. We're going to talk now about incremental elastoplasticity. We're going to talk about implicit constitutive solution. Last time we talked about explicit solution. And then before that, we had an introduction into plasticity. Implicit solution is one of the solutions that's available from the whole series of so-called midpoint rules. I'm not going to spend too much time with that. I need to introduce my colleagues, my co-workers, collaborators. I'm Boris Jeremic, UC Davis. Dr. Han Yang is a postdoc at UC Davis, and Dr. Heshen Wang is a PhD student at UC Davis. They worked on this and they developed many of the components that you see here, in addition to some other students before them. And so we'll continue with this lecture series over this whole month of April. By the way, sometimes I'll be posting these MP4 files, but I also post these PDF files, and sometimes some PDF viewers complain. So what I found out is that on all the platforms, on Windows, on Linux, on Macintosh, if you open PDF in Google Chrome, everything works. All the links, all the animations, everything works. So just use Google Chrome, or try anything else that you want. But we know we tried all Google Chrome, and everything works in Google Chrome. So let's go to this lecture again. Introduction. We talk about elastic plastic problem in computational mechanics. We define elastic plastic models through 4 components: elasticity, yield function, plastic flow directions, and hardening softening function. For a given increment in displacements, delta ui, 3-dimensional, we can find easily increment in strains. Again, these are small deformation strains. And now what we want to do in an implicit solution, we want to iteratively solve for a consistency parameter so that the so-called residual stress and, in some algorithms, or yield function are, or both of them, below certain defined small tolerance. So we can actually, with this algorithm, we can enforce equilibrium to within some small tolerance that we define. Once we find the actual value for consistency parameter delta lambda iteratively, we can then solve for incremental plastic strain, and we can solve for increment in internal variables. Again, loading process is incremental. We subdivide all of our loads carefully into loading stages: self-weight, construction, excavation, and so on, all sorts of stages of loading. This is really important for elastic plastic models because elastic plastic models do have memory. They will behave differently if you load them in different ways, in different stages. Each of these loading stages is subdivided into increments, and each increment, within each increment, we do iterations toward equilibrium to solve for that consistency parameter delta lambda. Once we go through all these loops, we eventually end up with an output that, hopefully, if everything was verified and validated beforehand, and if it was done properly, we can trust this output and make some decisions for design or for assessment. Again, review elastic plastic material models. We have to define elasticity, elastic stiffness. Those can be isotropic, anisotropic, linear elastic, nonlinear elastic. There are different types of elastic plastic models. You have to define yield function. It's a function of state of stress and internal variables. And that function defines if material is elastic or elastic plastic. If this function yields values that are less than 0, we say that material model is elastic. If this function is equal to 0, we say that material model is elastic plastic. We do not allow this function to be greater than 0, and that's why we have to go through these constitutive solutions or constitutive integrations. Based on this, we need also to find the plastic flow directions. We need to define plastic flow directions. Those are M plastic flow directions, and using those plastic flow directions, we can define the plastic strain based on the solution for delta lambda for plastic consistency parameter. Also, we can find the change, we can find an increment in internal variables based on this delta lambda and the hardening softening function that we define for material model, which makes us actually be able to find changes in internal variables. Again, this is for small deformation elastoplasticity. We talked about this in the introductory part. A small deformation elastoplasticity allows us to do so-called additive decomposition of strain into elastic strain and plastic strain. In lecture notes, there are also derivations for large deformation elastoplasticity. They are quite a bit more involved, but nothing special. You just sit down and work out details. I mean, but if you have interest, you're more than welcome to look up in lecture notes how this is done for large deformations. Again, this is all done for small deformations in current lecture. We know that we have defined elastic relationships, that those hold. We have plastic flow rule, and we have hardening, softening, hardening or softening rules that can be isotropic, anisotropic, distortional hardening, and so on. Again, we rely on Karush-Kuhn-Tucker conditions. There are 3 Karush-Kuhn-Tucker conditions. Yield function has to be always less or equal than 0. Plastic consistency parameter delta lambda has to be greater or equal to 0. And so-called loading unloading condition, product of F and delta lambda has to be equal to 0 all the time. These 3 conditions have to hold simultaneously. So that means if your yield function evaluates to less than 0, that means that you are elastic, because in that case, F times delta lambda has to be equal to 0. Therefore, delta lambda has to be equal to 0. Going one slide back, if delta lambda is equal to 0, there is no plastic strain is equal to 0, and there is no hardening softening. Changing internal variables is equal to 0. So that means that you have elasticity, your material behavior is elastic at the given location, at the given constitutive level. On the other hand, if you have elastoplasticity, that is obtained when F evaluates to 0. In that case, if F is 0, delta lambda has to be greater than 0. Going back one slide, that means that if delta lambda is greater than 0, this is predefined by model, this plastic flow direction, that will give us plastic increment in plastic strains that is greater than 0, or it is some, it exists, it's different than 0. And it's also going to give us an increment in hardening and softening internal variables. And so delta lambda being greater than 0 will give us plasticity. There's a special case when both F and delta lambda are equal to 0. That's a so-called special case, neutral loading. It happens very rarely. I've seen it only very few times if you instrument your code. So we will not spend time on that. In that case, for neutral loading, things are really happening elastically. F greater than 0 is not allowed. If F is greater than 0 not allowed, that means that this F is always equal to 0 for plasticity. If that's the case, then we can proceed and find out what is the value of consistency parameter delta lambda. So this is a similar plot from the previous case, except that now we actually do have a jump from previous loading or previous state of stress. We do a step up to predictor state. We evaluate predictor state. For this state, yield function is going to be greater than 0. Therefore, we have to do plastic correction. And in this case, plastic corrector follows this line. You might remember for explicit, it did follow this line. Now we follow this green line. And this is our new yield function. This line here is our new yield function at the state n+1 at the next step. And this yield function did harden a little bit from this state here at state n to state n+1. However, you note that our solution actually is on the yield function within certain small tolerance that we choose. It's a very small number, but we do try to make that tolerance small, not too small. I mean, there are some rules how to do it, and those are given in lecture notes. But you have to be very close to yield surface, and that's how you enforce equilibrium. Moreover, the actual plastic flow happens through a normal at the solution, the one that we don't know yet. That's why we actually have to perform iterations to be able to find this normal and this step size that's going to bring us back to the updated hardened yield function. So it's an iterative process that might take some time to be completed, but it gives us a much more accurate solution, and it also works for much larger steps. Again, but you have to do iterations. Again, the process is based on elastic predictor plastic corrector scheme, where in this case we go from plastic predictor to final solution, but we don't know this direction yet, and so that has to be done iteratively. Not going to go into too many details of how this is done. There's detailed derivation within lecture notes. We define a tensor of residuals, and then we try to reduce this tensor of residuals to 0, and we essentially iterate on this delta lambda and the m. So this is the iteration. We make changes to delta lambda, and here's how we start. We start with the previous value of yield function. These are normals to the yield function, and this is the actual tensor of residuals from the previous step. Going through these steps, not going to spend too much time on that because it defined the lecture notes. We end up with a so-called super matrix C, and that matrix actually has different formats depending on how many, what are the types and how many internal variables we have. In this case, we have no hardening softening. In this case, we actually have scalar hardening softening. In this case, we have multiple hardening softening tensors and so on. So for example, if you have a kinematic hardening, you're going to end up with a case like this. Again, this looks quite complicated, but it's worked out in lecture notes, and you're more than welcome to look into lecture notes and get details of how this is done for different types of models. Eventually, we end up with a so-called consistent algorithmic stiffness, the one that is consistent with the Newton scheme on the global level, and that stiffness allows us to have a very fast convergence. It is a little bit involved to get it to calculate this stiffness, but once you do this, it actually gives you very good iterative convergence. This method, again, implicit integration or so-called backward Euler, is relatively complicated because there's a need for first and second derivatives and inverse. So a lot of things have to be done internally. It's quite computationally intensive. It is relatively slow because all these computations that are done internally, but it does improve global Newton iterations significantly. And it does enforce equilibrium within some tolerance that you choose. Again, it's accurate because consistency condition is satisfied at the end within some tolerance that you control. It is actually unavailable in most codes except for simple material models like von Mises and so on. But again, it's designed to work with global Newton algorithm, and with that, it actually gives you very good convergence rates and gives you equilibrium at the end. Again, I'm not going to go into any details of this. There are full derivations and all the equations for different material models in lecture notes in section 104.4. So with that, I would like to invite you to look at Real Easy Simulator. All of these developments are implemented in Real Easy Simulator. There are a number of material models that are implemented using this implicit scheme, and you can look at those examples through realeasy.info here. And you can play. You have to spend time playing with these and trying different. There are different suggested tolerances and different material models, and you can play and see what you can, how much you can learn about how these material models and how these incremental iterative schemes work for different material models. Next lecture is going to be on the practical suggestions for elastic plastic modeling, and that's going to be in our next recorded lectures. So with that, thank you very much, and I'll see you next time.